Well, this is for Physics 2212, Lab 4, Magnetic Field of a Bar Magnet. So the purpose of this lab is to determine the distance dependence of the magnetic field of a small bar magnet. The main principles used was about Savart law. The system found was to be the magnetometer and the magnet, and the surroundings was found to be Earth. And then the result found that the distance dependent n is equal to negative 2.0011, and then the magnetic moment mu is equal to 13.342 amps times m squared. Here you can see what Bot's law states, where the magnetic field is equal to mu 0 over 4 pi, which is a constant, and that r is the distance from the magnet, and mu is the magnetic moment. Also note that when parallel or anti-parallel, mu dot r is equal to plus or minus mu, and when perpendicular, mu dot r is equal to 0. And so by doing so, this is also similar to the equation to find the electric field for a dipole. For the procedure, we first align the phone with north by having b of x equal to 0. Next, we locate the magnetometer chip. And then lastly, we measure the magnetic field at different distances. Here you can see what we observed at different distances. We then took our observations and then put them into a graph to see the distance dependence. By using the equation of the magnetic moment is equal to k, which is a constant, times the distance to the power of n. We then logged everything to get a linear equation. And then by doing so, we were able to find what n is equal, which is equal to negative 2.0011. And then by knowing what k is, we were able to find what the magnetic moment is, which is equal to 13.342 amps times m squared. Notice here that for n, we got something that is more similar to a point charge, which most likely means that we made a mistake when doing our experiment. During our experiment, the observations that we made was that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and also that as the magnetometer moves closer to the magnet, the measure x component of the magnetic field increases. Here is our glow script code. Notice that we use Bot's law in our dipole B function to define it. And this is the rest of the code where we pretty much just make vectors on the axis and perpendicular to the magnet. And here's the result of our glow script code. You can see that the yellow vectors represent the magnetic field on the axis. The blue vectors represent the magnetic field perpendicular to the magnet, and then the purple vector represents the magnetic field at a 45-degree angle. I would say that this is a better depiction of what the magnetic field looks like because, again, we found that our magnetic field was more similar to a point charge when it's supposed to be related to r cubed instead of r squared. The assumptions that we made during the experiment was that we assumed that the bar magnet acts as a magnetic dipole. And then the potential errors that we may have had was that the environment may have affected collected data, like if there was metal or other magnets nearby, which could have affected what our result was. The first what if question is that if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field, how would your results have changed? Well, then Earth's magnetic field would have affected our results for X and Y. And to remove this, we would have had to do more calculation to subtract the X and Y found for Earth's magnetic field. And then the second what if question is that if you were to stick two identical magnets together end to end and run the experiment again, how would you expect your measurements to differ? Well, based on the superposition principle, it would have just been one magnetic field from one magnet plus another magnetic field from another magnet, which would have just doubled the magnitude of magnetic field. And so to conclude, we use Bot's law to find the magnetic field of a magnet.